I have a delivery assignment for you today. Please get it done in 40 minutes.
Hmm, this route usually takes about an hour. How are we going to get it done in 40 minutes?
Ah, this looks like a case of a traveling salesman's problem. I don't know much about it, but let's take a look.
So what we want to explore is the traveling salesman. Let's say that we work for Tito and we start the stud and we have to deliver Boba to people all around campus, whether it be the Course One Lounge, where I live across the river, or all the way down to next house. You obviously don't want to walk more than necessary, so we should try and figure out what the best way to get around MIT's amazing campuses. Perhaps the simplest method of approaching this problem would be the gritty approach. We start at Tito. We want to deliver that boba as fast as we can. So how about we just go to the next delivery location that's closest and get it to that person the quickest. We can see that if we start at the stud at node 1, the next closest node would be the Course One Lounge, which is node 6. So we go from 1 to 6. Looks like we look at all of the rest of the nodes. The next closest node is node 5. Finally, the only node we haven't visited is across the river, node 7. And then we have to return to our starting location. And it turns out, if we sum up all of these edge weights in smoots, we arrive at 1896 smoots. This works, but we can kind of start to see that there's a little bit of inefficiency. So we want to compare maybe some more possible paths than that just greedy path that's just like the logical first path to come up with. So what we can do is literally just brute force, let's calculate every single path. So here's some example code to think that through. So here we've represented that exact same problem that you saw on the graph I was just showing you, just in matrix form, where all of these are edge weights, just distances and smooths, because we don't want to walk that far. We're lazy. And what we do is we have a handy tool that allows us to get the all of the possible combinations, all the permutations of numbers 1 through 7, so that we can look at all possible paths. And basically, we're just going to calculate the total number of, total walking distance, total cost associated with each route, and just return that path and the cost of that path. And we do actually get a much lower cost using this method than with the greedy method that I just described before. So demonstrating that that greedy method isn't always very optimal. But we can start to realize that this method, while it does allow us to see the path, the costs associated with all paths, there's n factorial paths, right? Because if we start at Tito, that's one node out of, in our case, only 7. We have 6 on our fully connected graph. We have 6 nodes left to choose from, then 5, and 4, etc. So calculating the cost of all these paths and comparing them is going to start to take a really long time if we do have a much, much larger graph compared to this simple one that we've created here.
Well, what about the 2-up method? So just to explain how this method works, basically we would select 2 edges, let's say this edge and this edge, and replace it with 2 other edges to complete the tour. So the 4 nodes that we're looking at would be these 4 nodes. So if we erase this edge and instead replace it with these edges, we would have a different tour. And from there, you would calculate the difference. So you add up these 2 edges, compare it to the previous 2 edges to see which one would end up with the least distance. And you iterate through that with 2 different edges each time. And from there, decide which tour would give you the local optimal.
Now, going over the time complexity of the algorithm, this is a summary of what the algorithm would look like. And if we pay attention here, defining a random tour would take about a time complexity of O of n. And we have a double for loop here, which would make a time complexity of O of n squared. And then evaluating D2 could range from taking instant or taking up to O of n, depending on how different the tour is once the edges are swapped. Hence, the overall time complexity ranges from about O of n squared to O of n cubed. Now, if we are looking at an initial tour of Tito, Newvassar, Next, CE, TT, Baker, McGregor, and Tito with the following numbering system, the original distance that we get would be 2,407 smoots. And by running the 2-op algorithm, we get an improved distance of 1,798 smoots, which is an improvement, but not the global optimum.
Now that Eve explained the 2-op method to you, we're going to explain a method that guarantees the optimal solution. This is dynamic programming. We're going to start off with defining the states, where we define S, a set containing the reference node Tito, and J, a node outside of the set S. We're going to go in stages like we did in class, with the stage being the number of nodes in S, the reward being more of a penalty, the distance we travel on the next step, and the value function being this value function, which is the minimum length path where we start at J, visit all nodes in S, and end at the reference node Tito. The value iteration is going to go something like this. If we want to find the value for set S, node J, we're going to iterate over all nodes S inside of S, where S is not equal to the final node Tito, incur that penalty, and then solve the subproblem with S, the set S, without the node S. So just to give an illustration, if we look at this graph down here, what we can do is we can start at this node J and then do casework on which of the nodes in S we choose. So one case might be that we go all the way out to this node, and from here, we're going to solve the subproblem where we replace J now with this new starting node, S, and now we solve the subproblem with the new subset. And we keep on recursing down using value iteration, and finally, we'll arrive at the optimum.
We want to start at Tito and come back, but again, we cannot really make any subtours, but at the end, we're going to make that tour, and we have a couple of constraints. So we have essentially, we want to minimize the cost given our data, in this case, the edges of the smooth, that is C. We have the binary variable Y, which essentially it considers or not the city. In this case, instead of a city, it's a location in the graph. We have the first two constraints that say for every incoming edge, there's only going to be one coming to a particular location. And there's also going to be one particular edge going out from that particular location. So CE will have only one edge coming in and out. And the last one, we say that the number of edges, it has to be, in our subset, it has to be less than the number of locations in our subset minus 1. Not including, of course, the initial subset that is empty since we don't really have any locations. And the last one, since we actually need the same amount so we can actually go back to the same, in this case, Tito. We can make the tour. Binary decision variables, as I mentioned. And essentially, the path is, we start at Tito, Newvassar, Next, McGregor, Baker, TT, CEE. And then we head back to Tito. And, well, we get similar to some of our other friends, 1785, but I guess the importance is, as the size of our graph expands, optimization can really yield the n squared times 2 to the n. But ideally, it might be a little bit faster than DP in some cases.
James, look, we did the run in under 40 minutes.
In fact, we did it in 1,785 smoots to be exact.
Great. Now, here's a delivery to Harvard dorms. Be back in 40 minutes.
Not again.